Hello, everyone. For this journal club, I will present the topic of bimetallic nanoparticles as a biosensors. My name is Carlos Alberto Marquez Ibarra. So let's jump into the content. First, a brief summary of this presentation. I will start with a little background of this topic. Then I will start with the methodology of this paper, which is basically the synthesis, functionalization, and experimental setup of the biosensor. Then I will explain the experimental results that are basically the characterization of the nanoparticles and the sensing performance of this biosensor. Finally, I will summarize the conclusions of this paper, and then I will give my critical analysis of this article as well as the possible future work. This is the paper that we are going to discuss today. The title of this article is Surface Plasma Resonance Biosensor based on magnetic gold nanocomposites. And it was conducted by Wang Jian and their collaborators back in 2010. This work develops a biosensor based on surface plasma resonance of nanoparticles to detect the concentration of the antibody human IgM. This surface plasma resonance biosensor takes advantage of the gold plasmonic properties as well as the magnetic properties of magnetit to generate a sensing membrane that are made from functionalized nanoparticles and can measure the antibody concentration via shifts in the surface plasma resonance spectrum. We will discuss more about this later in this presentation. But first, let's talk a little bit of context. The difference between an antibody and antigen is that an antigen is a substance that can induce an immune response. They are usually made of proteins, but they may also made of other organic compounds like lipids or nucleic acids. An antibody are proteins that recognize those antigens, bind this antigen to produce an immune response. As we can see, basically an antibody is attached to certain antigen and produce an immune response in certain organism. For example, when we enter in contact to a virus or antibodies getting attached to the antigens of the surface of this virus and generates an immune response. Now let's talk about surface plasma resonance. Surface plasma resonance is a phenomenon produced at the metal surface layer, where under influence of an incident light with a certain energy and a certain incident angle, the conducting electrons oscillate collectively. This causes the polarization of the material. This phenomenon takes place on when you have incident light wavelength is considerably bigger than the dimension of the given material. One of the most famous examples of surface plasma resonance are the gold nanoparticles, which exhibits a strong surface plasma resonance when you measure the absorption spectrum of those nanoparticles. For example, if you observe the absorption spectrum of gold nanoparticle, you can see different absorption spectrum depending of their features. Sorry, for example, size or the shape of the nanoparticle. Here in this image, we can see how different shape of nanoparticles produce different absorption spectrum depending of the dimensions of these nanoparticles and the shape, especially the shape of the nanoparticles. For example, for spheres are the black line. We can see that only contain one peak, surface plasma resonant peak, that represent that this nanoparticle will absorb light at this specific wavelength, and otherwise it will not absorb really well. But in the other hand, we have nanorods, which are elongated shape. In this case, we have two surface plasma resonant peaks corresponding to their dimensional axis. We have the longitudinal and the transverse peak that are represented here. But if we have more complex geometries or shapes like prism, we will get more complex absorption spectrums. Now let's jump into the paper. The paper starts with the methodology of this paper, but this starts with the synthesis of core shells. The core shells in this paper were synthesized by two main steps. The first step is generates the iron oxide nanoparticles. This was prepared by the chemical co-precipitation method. This method is basically consists on the precipitation of two iron sources. In this case, iron 2 plus and iron 3 plus by adding a base, in this case, sodium hydroxide under a nitrogen gas protection. This gives as a result iron oxide nanoparticles or magnetite nanoparticles is the same. These magnetite nanoparticles were dissolved into the solution, and this solution were added with chloruric acid, sodium citrate, and MPA compound, which is our ligand compound that will be important in the functionalization of these nanoparticles. So doing so, you get a solution of core shells nanoparticles that can be functionalized due to the presence of this MPA compound. So now let's jump into the functionalization part. As we mentioned before, the MPA compound play a key role in the functionalization of these nanoparticles. So in order to functionalize the nanoparticle, the carboxyl group of the MPA composite surface was activated with NAS under the catalysis of the EDC compound, sorry. After this activation, the carboxyl group can react with the amino group of the protein of the antibody. Then desired concentration were introduced into the nanoparticle solution to conjugate the nanoparticles and enables the antibody detection. Once the functionalized nanoparticles were introduced into this sensing cell, and these nanoparticles were attracted by this magnetic pillar, forming this sensing membrane at the surface of a gold film, followed by a chromium film. These films were excited with incident light that was focused with the prism under the Kirschmann configuration, achieving the resonant condition by attenuating total reflection. And the prism was coated with these layers of metal films. So when you add the concentration of antibody, this generates a change in the detection signal, generating the shift of the surface plasmon spectrum that enables the concentration measurements. Now let's talk about the results. The results are basically starts with the nanoparticle characterization. On the left side, we see the UV spectrum of all the nanoparticles. In this pink line represent the magnetic nanoparticles, and the other curves represent the core shell structures with different diameters ranging from 8 nanometers to 30 nanometers. And on the right side, we see the same nanoparticles, but we see the transmission electron microscopy images when we can see the morphology of these nanoparticles and their dimensions. Oops. Now, this is the most important part of the results, is where they compare the performance of the SPR biosensor by the different size of the nanoparticles here in the left side image. So basically they compare the shift in the plasmonic and the shift in the surface plasmon spectrum. These shift are compared by different sizes of nanoparticles. And in the right side, we see to make sure that this biosensor effectively detect the presence of this specific antibody. We were tested with 2 other antigens. They tested with bovine serum albumin and human serum albumin. And as you can see, with these other antigens, it didn't show a significant response with this antigen. That means that effectively the functionalization of these nanocomposites uh, uh, detect the attached to the antigen that we want to measure, and it generates a wavelength shift significant higher than the one that we measure with the other antigens. Then, based on these results, the author concludes that core shell nanocomposites modified with MPA present good biocompatibility and exceptional optical properties. Then they also conclude that the magnetic properties of iron oxide cores allow the immobilization of the regeneration sensing membrane, which is important to have a constant signal from the biosensor. And they also conclude that there is a specific size of nanoparticles and MPA concentration or ligand compound that optimize the detection of certain analytes. So if we want to measure another analyte, you need to tailor the size and the ligand compound to optimize the biosensor sensibility. Now I will give my critical analysis of this paper. I consider that overall it's a really good article, but I think there is some things that they could explain a little better, or maybe they assume that the lecturer already known that. So their strengths are the bioconjugation explanation. I think it's really complete and really well explained. Then the role of the sites and the ligand compound in the biosensor sensibility. I think they explain really well how the size of the nanoparticle and the ligand compound plays a key role in the biosensor sensibility. Finally, the performance of the resultant biosensor is really impressive. They effectively measure different concentration of this antibody in an acceptable range of concentration. But in the other hand, we have the limitation or the things that I think the paper could explain better is explain with more detail the experimental setup, especially the optical setup, because they didn't mention where the magnetic pillar were placed or how they perform the angles of the optical array, but I think it's not super hard to find. But I would like I would like to they explain better this part. Also, the complexity of the experimental setup, I think is it could be a limitation of this paper, because this experimental setup also contains several parts, as all the metal surface, as well as the magnetic pillar, the optical array, the sensing cell. So I think there is another, it should exist another way to simplify a little bit the experimental setup, but I think it's still really good experimental setup. Finally, I would like to see a little more quality in the TAM images, because TAM allow you to see the different parts of the nanoparticle. So more resolution images maybe will allow us to see the different parts of the core shells. But I think the images are actually really good still, because the scales that they handle are really small. They are nanoparticles about 8 nanometers to 30 nanometers. So I think it's enough quality to that scale. So now for future work, I think that these are the possibly future work that could result from this paper. Are first the sensibility improvements of the optimization of other components of the biosensor, for example, the metal surface, for example, the gold surface. It could be explored the role of the thickness of these films, and the morphology, the surface, the morphology of the surface, to improve the biosensor sensibility. Another future path could be the medical application of this technology to the detection and treatment of different disease. And finally, it could be helpful to have theoretical work that enables the discovery of new nanostructures that help to improve the sensitivity of the biosensor and be able to sense a wider variety of organic compounds and even lower concentrations. For example, maybe a trimetallic nanoparticle, or different shapes, or something like that. But I think there is too many possible application to this work in different fields. I hope you enjoy this journal club, and that's all for my part. Thank you for watching this journal club.